Assalamu alaikum and welcome to our channel. I am Dr. Hamad Ismail. Today we will talk about protein DNA molecular dynamic simulation using Gromacs. Protein and DNA require the separate force field for the molecular dynamic simulation. In this tutorial we will guide you that how you can select the appropriate force field and perform the molecular dynamic simulation. In the later part of the video we will explain that how you can perform the analysis on these MD trajectories. So let's start. First of all, you need to install the Gromacs. If you are the Linux or Ubuntu user, then you don't need to install the WSL. Otherwise, you also need to install the WSL. This is the complete command line which I have prepared. The complete tutorial for this installation is also available on our YouTube channel. I will also provide the link in the video description section. First of all, you need to open the PowerShell. Then you need to update the WSL. After updating the WSL, you need to restart your laptop. Then install Ubuntu using Microsoft Store, and WSL will be installed in your laptop. After installation, update your system using these commands and then install the dependencies for the Gromacs. After this, download the Gromacs 2025. After this, install the Gromacs. After installing the Gromacs, you need to source the Gromacs and make it permanent. You can use this command. Then install the Python requirements, because Gromacs only work with the Python 3.5 and 3.7. In this tutorial we will use 3.7. Then you need to install the Python version manager. This will create a new environment. We need to fix it using these commands. After this, you need to install the Python 3.7 and then make an environment in this Python manager. After installing the Python manager, we will source our environment and we will activate our environment. In this environment, we will install these packages: pip, numpy and network_xx. These are specific requirements for running the Gromacs. If you do not justify these requirements, you will be unable to run the Gromacs. After running, you can check your installation using these commands. I will also upload all these commands on my GitHub, and the GitHub download link will be provided in the video description section. This was the quick upload. If you need the detailed step-by-step installation, please refer to our video by using the link provided in the video description section. Today we will use the complex 1A1F, which is basically the zinc finger DNA complex. This is zinc finger protein and the DNA complex. You need to simply download this file as a legacy PDB format. The file will be downloaded. This is my file. I will open it in the Discovry Studio. You can see that it has some water molecule. Then it has a protein and 2 chains of DNA. So basically 3 chains and water molecule. First of all, we need to go to the script, go to selection and select water molecules. Once the water molecules are selected, press on the delete button and all the water molecule will be deleted. Then we also have some heteroatom over here. Select it and delete it, and this one select it and delete it. Again over here I can see this is another atom. Select it. After this, rotate it and see if there is any other heteroatom present in this protein ligand complex. So these are basically 3 chains. You can click on this arrow and you can see this is one of the DNA chain. B and C is also another DNA chain. One is the sense strand and other is the antisense strand, and the third is the protein chain. So rest of the water molecule has been deleted. Now go to the file and click on the save as button. Select the molecule as protein PDB and save it as clean PDB. CLEA and clean.pdb and save it into the current working folder. If you are familiar with Discovry Studio, it is good you can perform it very well. But if you are not familiar with the Discovery Studio, we have another video tutorial just focusing on the Discovery Studio. I will also provide the link in the video description section for Discovery Studio. Now go to the start button and click on the Ubuntu, search for Ubuntu and open Ubuntu. Our Ubuntu is now open. This is the window. I have created a folder on the desktop with the name GMX. In this GMX, I have placed my file clean.pdb on which I am going to work. First of all, I need to access my folder from the desktop. For this, what can I do? Simply open this folder, click on the address bar and Ctrl C, copy it, paste it any editor or something like this. This is basically your path. We need to modify this path according to the Linux as we are using the Ubuntu version. Let me do that. Simply here, first of all, change all the backward slashes to the forward slashes. This is your path. Backward slashes to forward slashes. Then remove this colon and make C small. C is basically your current drive. It may be D, it may be E, but whatever the drive is, make it small. Then type mnt / and at the start type cd and space. After doing this, copy this complete command, go to your Ubuntu and paste it and press enter. Well, it come up with the error. Let me check again. Okay, we have missed some one forward slash. Then I have completed it. Copy it again, go to the Ubuntu and paste it. Now you can see you are now in the GMX folder. Type ls. You can see I have this file and also have clean.pdb file. So we are now in the correct folder. After entering into the folder, we need to activate the environment. This is the environment I have prepared using the Python Gromacs environment, which I explained earlier that we are using the same environment which we prepared in the installation tutorial. So copy this command and paste it in the Ubuntu terminal. And now you can see you are now in the correct environment. Once you have entered in the environment, now we are going to use the Gromacs pdb2gmx command, in which we are going to use the clean.pdb which we have just used, and it will produce the process.grow and it will produce the topol.top, and we are going to navigate each step one by one. Before running this, I want to explain that in this current scenario, I am going to use the complex in which protein and DNA is already binded. But if you have your DNA separate and protein is your separate molecule, you can simply download your protein, you can download your DNA, and then you can perform their docking. After performing the docking, you can use the complex, which means you can save them as a single file, DNA and protein as a single PDB format, and then we have also made a tutorial on which you can perform docking of DNA with the protein. The link is also provided in the video description section. So once you have a complex DNA plus protein as a single PDB format and you have saved it as rename it as a clean.pdb, then copy this command, go to the Ubuntu terminal and paste it. After pasting it, press enter. When you will press enter, it will come up with all the force fields which are available in Gromacs. Here we are interested in number 6, which is Umber 99 SB ILDN protein and nucleic Umber 94. So it is the mixture of two force field, one force field for Umber 99 SB which is for protein and Umber 94 which is for nucleic acid. So simply type 6. It will handle both the part, the protein chain as well as the nucleic acid chain. Press enter. When you press enter, it will ask you to select the water model. For this, we are going to use the tip 3P, which is tip 3 point, which is normally recommended. Type 1 and press enter. It will process your all chains and it come up with the, if the command is successful, it will come up with the quotation. If Gromacs come up with a quotation like Gromacs remind you, it means your command has been executed successfully. If you look into your working directory, let me arrange it sort by date modified. You can see it has produced ITP files, then it produced topol.top, it produced process.grow, and it produced protein chain A ITP, and then DNA chain C and DNA chain B. It has automatically identified the protein chain and DNA chain and produced their ITP files. And it also produced process.grow, in which we are going to use it in the next step. In the next step, we are going to define the box in which we are going to use process.grow, and it will produce the box.grow, and we have assigned it the value 1. 1 mean it will assign a value about 1 nanometer box for the dodecahedron, which is a flexible and efficient bond for the DNA. Simply copy this command and go to terminal, paste your command and press enter. You can see it has generated the box, which is the box vector is this, box angles are this, box volumes are this, and center are these, etc, etc. The Gromacs quotation appeared, it means the command executed successfully. After defining the box, the next step is solvation. For this solvation, we are going to use the command of solvate, and we are going to use the box.grow, and we are going SPC 216 grow and solvated, and we will choose the topol file. Simply copy this command for the solvation, go to the Ubuntu terminal and paste the command and press enter. And you can see that it has generated the volume, density and number and process. It says that it has generated 8973 solvent molecule with the res name solvent, and it automatically added in the topology file. The Gromacs remind you, it means your command has been executed successfully. The next step is preparing the ion inputs. For this, copy this command nano-ions.mdp, go to Ubuntu terminal and press enter. You will be promoted into next window. In this window, copy these two lines, paste it here, press Ctrl O, press enter and press Ctrl X. The file has been saved. After doing this, we have generated a ions.mdp using this command prompt. Once you have generated it, simply generate the TPR file. For this, we are going to use grom pp ions and ions.pd, solvated.grow, topol.grow and ions.tpr. Copy this command, go to Ubuntu terminal and paste it. And the command has been completed successfully. If you look into the installation folder, we have just generated this command. You can see you can also generate it manually by using this. We have added these two lines in that file. I will also provide all these files which you required using during the Gromacs MD simulation steps. The next step is adding the ion. For adding ion, we can make it neutral by adding sodium or chloride ion. Sodium ion provide the positive charge and chloride ion provide the negative charge. Simply copy this command, go to the Ubuntu terminal and paste it and press enter. It will be promoted into the next page to choose the solvent molecule group. Here we are interested in the solvent group. Simply type 14 for solvent. If your number is different, you just need to choose the solvent. Type solvent, press enter. And the command has been completed successfully. It says that replacing molecules with Na and chloride ion. Now we are at the energy minimization step. For energy minimization, we need to create em.mdp. For creating this, copy this command nano em, go to Ubuntu terminal and press enter. You will again promoted to gun nano. In this, copy these all colored lines up to this, paste it this terminal, press Ctrl O, press enter and press Ctrl X, and you will see in your installation folder that em.mdp has been generated, and it contains all that information we have just added. I will also provide this file as the download link. After creating em.mdp, first of all run this command for energy minimization parameter. It will adjust the energy minimization parameter. The parameter has been successful by adding. After this, run the energy minimization step. For this, I am going to copy this command and paste it in the Ubuntu terminal and press enter. You can see it has been started the energy minimization steps for all the frames that are available. Energy minimization has been completed. Now we have to perform the equilibrium using the NVT. For this, first we have to create nvt.mdp. The procedure is the same. Simply copy nano nvt.mdp, press enter and copy these commands up to this and paste in your gun. Press Ctrl O, press enter and press Ctrl X. After this, we are going to add the parameter for NVT. For this, copy this command. It will fix the parameter. The job is completed. After this, copy this command for NVT run. Copy this one and paste it. I have added -b version. If you add -b version, it will give you the remaining time. It will take about 10 to 15 minutes to complete this job. Meanwhile, it completed job. Let me explain one thing more. When you copy this into the nvt.mdp, this step is crucial, which is ns step 50,000. When you select the ns 50,000, these are basically ns 50,000 step. It corresponds to 100 picosecond. For demo version, I have selected 50,000 step, which correspond to 100 picoseconds. If you are and I will at the end I will perform MD simulation only for 1 nanosecond for the demo purpose, but when you are doing the real MD simulation, you need to change it to the 1000, or you can increase the zeros. You can choose the 1000 picoseconds, or you can use 1 nanopicosecond. If your target is 100 nanosecond, you can change it according to your need. What you can do, you can simply go to this folder. This is nvt.mdp. Open this, and these are the nano steps. Just increase the zeros as much as you like, and then save it and rerun these commands. Rerun these two commands, parametric files and then the simulation file. Now our NVT is under process and it is running. Once it completed, we will move to the next step. Our job has been completed. Now we have to perform the MD at npt, and first we have to create npt.mdp. Simply copy this command, go to Ubuntu terminal, press enter, and you will be directed to gun nano 7.2. In this, copy all this colored line present in this file. Up to till, copy this and paste it here. Press Ctrl O, press enter and press Ctrl X. The npt.mdp has been created in your working directory, and you can see this is all the content we have just pasted, and this is the ns step, which 50,000 step, which correspond to 100 picosecond. If you like, you can increase or decrease as per your need. After doing this, save the parameters, copy this command, go to Ubuntu, paste the command and press enter. The parameter for this npt has been saved. Next we have to run the empty MD simulation. For this, copy this command and paste it in the Ubuntu terminal. After pasting it, press enter. It will start the npt MD simulation. The npt simulation has been initiated. It will take about 20 to 30 minutes to complete the job depending upon your computer speed. Our npt run has been completed. Now our last step of MD simulation is MD production. For this we need to create md.mdp. For this, copy this command, go to Ubuntu terminal and press enter. Here paste all these colored lines up to this and paste into gun. Press Ctrl A, press enter, press Ctrl X. In your working directory you will see that md.pdb has been created and it contains all the information present over here. Right now I have set it for the 1 nanosecond for the demo purpose. If you want to run it for 100 nanosecond, just increase 2 zeros and it will correspond to 100 nanoseconds. After this, save the parameter file for the MD production. For this, copy this one, paste it in the Ubuntu terminal and the parameters have been saved successfully. Then run the production. Copy this command and save it. It has started the production. It will complete. Then we will move to the next step. For the demo purpose, we have switched it to 1 nanosecond only. Our MD production has been completed. As you can see, the Gromacs remind you code has been appeared. After completion of MD, you can go to your working directory and you can see the md.xtc has been generated. These are basically your trajectory files, and md.grow, these are basically your topology files, structure topology files. So now we will move toward some basic analysis. For this basic analysis we are going to use the RMS. We are going to calculate the RMSD value. Simply copy this command, go to Ubuntu terminal and paste it and press enter. It is now asking you about for which group you want to calculate the RMS. Either you want to calculate the RMS for DNA or either you want to calculate the RMS for protein. Right now for demo I click on 3 is my protein and press enter. Then again type 3 and press enter. It is now calculated the RMSD. The result has been generated. You can see the quotation has appeared, which means my command has been executed successfully. I have given its name the RMSD.xvg. You can also change the name here like protein RMSD or DNA RMSD and so on. You can go to your working directory and you can see this is RMSD.xvg, and you can see these are your result of RMSD value. You can open this file in Excel and can prepare the graph. The other way to visualize the result, you can use XMGrace. Grace is a small software which is used to utilize the graph. When I type the Grace, if you are already installed, it will give you some output. If not installed, it will suggest you can install it. Simply copy this command, sudo apt install Grace, and paste it here and press enter. Type your Ubuntu password and press enter. This is typically a small software. Click on type yes and press enter. It will install this software and then we can use this software for visualization of RMSD, RMSF and so on. The Grace package has been installed. What you can do, you can simply do, this is the name of file rmsd.xvg, and you can use simply xmgrace rmsd.xvg, which means you will type xmgrace and name of the file you want to view. Simply copy and paste and press enter. It will pop up with the new graph menu. You can calculate, you can see the RMSD. Here this is the 1000 frame and 1 nanosecond. This is the RMSD of the protein we have just generated. In the same way, you can generate the RMSD for DNA, and then you can calculate the hydrogen bond. This is the information for the hydrogen bond, protein and DNA. Copy this command, paste in the Ubuntu terminal and press enter. Now it is asking you about the groups for which you want to calculate the hydrogen bond. Simply here I am going to first use the DNA number 1. I am going to type number 1 and press enter, and then I am going to use the protein number 3, type and enter. Now it's calculating the hydrogen bond between the DNA and protein, and the job is completed. After completing the job, you can simply type xmgrace hydrogen bond. Hydrogen bond is the name I have just placed. Copy, paste and press enter. You can see these are hydrogen bond between the protein and DNA up to 1000 frames. Now the next point of analysis is our RMS. RMS is basically root mean square fluctuation. For this again we are going to use this command and then paste it and press enter. Here we're going to use the number 3. Number 3 is our protein. Type 3 and press enter, and it is going to calculate the root mean square fluctuation for protein. You can also calculate for DNA. Then here I have calculated the root mean square fluctuation for protein. I am going to use xmgrace to view the graphs and press enter. You can see this is the root mean square fluctuation of our protein up to 2000 atoms, and these are the fluctuation parameters. Then we can calculate the radius of gyration. For radius of gyration we are going to use the gmx gyrate command. Again the gyration for the protein and press enter. Here I am going to use number 3 for protein, and it is now calculating the radius of gyration for the protein. The job is completed. After completing the job, we can view the graph of radius of gyration and then press enter. This is the radius of gyration of the graph for protein. Then we can calculate the solvent accessible surface area, for which we are going to use the SASA. For this I am going to copy this command and paste it here. Here we are going to use, again we are going to use 3 for protein, and now it is calculating the solvent accessible surface area. Job is completed. Solvent accessible surface area has been completed. Now we are going to copy it and press enter. This is a graph for solvent accessible surface area. You can view it. Close this command. The basic analysis has been completed. If you go to the folder, you can see different kind of H-bond XVG, RMS XVG, gyration XVG, solvent accessible surface area complex XVG. You can simply open this file with the Excel sheet and you can make the graph. One more important trajectory analysis I would like to explain here. If you are interested in average PDB of complete MD simulation. For this, first of all, we are going to remove the rotation and translation angle from the trajectory. And For this we are going to copy this command, paste it in folder and press enter. It is asking for the list group for square item. Here we are going to use the backbone number 6 backbone, and then it's asking for the output. For the output we are going to use system is 0 and type 0 and press enter. Now it is removing all the rotational angles from the trajectories. Once all the rotational angle has been removed, then we are going to use this command to generate an average PDB. The output will be avg.pdb. Copy this command, go to Ubuntu terminal and paste it and press enter. Here we are again going to use the 0. 0 is our system, which means system contain all atoms which contain water molecule. This contains sodium and chloride ion, DNA as well as RNA. And click 0 for system and press enter. Now it will generate our output file. It has generated the file. You can go to your system and you can see it has generated the average.pdb. You can simply open it in the Discovery Studio. This is average PDB. As I told you earlier, this is basically the complete system file. It also contains water molecule and the other molecule. You can simply go here, click on this icon and click on the chains, so it will remove the other molecule. You can see these are basically the protein chain and the ligand and protein chain. You can also extract the specific frame you like. These are the chain A, then chain B and chain C. These are the different chains. You can view different view. You can view nucleic acid or the protein groups you can see. You can also view this in your PyMol. This is our PyMol. Go to the file, open from desktop into GMX. In GMX we are interested in avg.pdb. Open it. You can see this is an average PDB structure. You can view its angle and many more things. You can also see the sequence. It also contains water molecule and so on. If you want to to perform more advanced analysis like MMPBSA, like free energy landscape analysis, you can visit our channel. We have a complete playlist for Gromacs tutorials in which we have already performed all these analysis in a very simple way. So this is all about today. If you have any question, you can ask in the comment section. Please like and subscribe our video. Thank you so much for watching. Allah Hafiz.